Welcome everybody to the 5th unit of the 5th week in the Parallel Programming Concepts course. We meanwhile discussed the idea of shared nothing environments and hardware, the idea of interconnect topologies, and the question of how to choose the right task granularity in your parallelization problem. We also have shown you how to do parallel programming in the shared nothing environment with MPI or the channel concept. And in this unit, we now want to introduce another interesting parallel programming paradigm, which is called the actor model. The actor model was originally introduced by Carl Hewitt and some co-authors in '73. And this is another mathematical model for concurrent computation. We saw several of them meanwhile. And in this model, we have a basic primitive, a basic concept, which is called the actor. And an actor is a computational primitive that is able to perform some local computations. So this would be something like an application instance running on one of the nodes in our shared nothing environment. And this computational primitive makes local decisions. And based on these local decisions, it either sends or receives messages. So until here, this is very common to what we have already seen with, for example, MPI or the channel model. The interesting aspect about actors is that they behave a little bit more dynamically than the other models we saw so far. So with actors, we have a concept that is called a mailbox. So when an actor receives messages, there is no blocking receive call that waits for an incoming message and which acts as a synchronization point, but instead we have a mailbox. So in this mailbox, all the received messages are collected while they float into the actor instance. So whatever comes from other actors as a message is collected automatically inside the mailbox. So the actor can check this mailbox in the control flow when it's actually the time to do that. We still have one-way messaging here. But the message sending is asynchronous. So a send operation for an actor is something that immediately returns. So we have the situation here that in comparison to the rendezvous model in CSP, this is more dynamic and more asynchronous. So the sender sends out the message and immediately continues with its own workflow, while the receiver has a reception mailbox, which is checked from time to time when inside the control flow it is the time to react on external messaging. The trick here is that this is a better decoupling of timing behavior, so you get less probability for race conditions because both sending and receiving are more decoupled from what is going on with other actors. The recipient of a message in actor communication is identified by a mailing address. So you have some kind of global identity, similar, for example, to the MPI rank. This is already part of the main concept, and it allows you to send identifiers for actors to other actors. So you can create new actors in your system, you can take their identity and hand it over to other actors in order to allow them to communicate with them. This gives you, again, a more dynamic behavior inside your parallel application in the shared nothing environment, because you now have the possibility to create fresh actors and to let them participate in the overall communication of your system. Actors were a theoretical concept for a long time, but meanwhile, today we have the situation that they're established in a lot of programming languages, so they are available either, for example, as extension, as with Java, or in completely new languages, such as with Scala. And this gives you a couple of possibilities to actually reuse this concept for your parallelization. One of the first languages that made the actor concept really popular in the software development was Erlang. Erlang is the shortcut for Ericsson language. So this is a functional programming language that has inbuilt actor support. It is designed for large-scale concurrency, not necessarily for running parallel applications. The first implementation was made public by Joey Armstrong in '98. So since then, this is open source, and as you can see, this is a comparatively old language. And the original language goals were driven by the Ericsson product teams and by their requirements on the development platform. So what they needed was a way to write software in a way that it's ultimately scalable on a lot of machines, on a lot of resources. In their case, it was about phone call handling in software. they needed fault tolerance inbuilt into the language as a primary construct, and stuff such as software update, but also scalability and the solving of concurrency issues. And as you can see on the slide, there are many users now, many systems that rely on the scalability features of Erlang, and so it is interesting to see how they leverage the actor model, the formal idea, in order to achieve all these goals. So in Erlang, the concurrency is following a set of basic principles which are called the concurrency-oriented programming principles. They mostly come from the original actor idea, such in a way that actor processes are completely independent. So they have no shared memory, no shared state, only local state. All the synchronization happens over message communication. You have unique identifiers, and the default approach is fire and forget. So an actor is sending a message, immediately returns, and then it doesn't know whether or not the message arrives, but it can continue with its own operation and see if some reaction in the system, for example, an answer message is floating in later. We have the mailbox concept on the receiver side, also in Erlang. So the receiving actor in Erlang can check its mailbox if a particular information is available or not. If you use such a model where you have completely decoupled activities, only relying on messaging, this gives you interesting opportunities. We see that also later with the MapReduce examples. The decoupling allows you to have a very good scalability. So just adding more machines to your shared nothing environment gives you the opportunity to run more actors in parallel. You have latency issues with the distribution, but that's the only penalty you pay. And you get an easier fault tolerance, because when nodes are going down, you can respawn the actors on other nodes because they only rely on the local state. So as long as you can deal with the local state of the actors, you don't have to shut down the overall program with all its parts. But if one of the parts in a cluster is going down, then you only have to deal with that one and can let the others simply wait for the according information from the failing node. Actors in Erlang, since this is a functional programming language, the syntax is a little bit uncommon maybe for most of you. Actors in Erlang are implemented in a way that you have communication as basic language primitive. So you have the exclamation mark, similar to CSP-style languages, that allows you to express a sending operation. Here, PID and message, so we send a message to a particular actor PID. We have the mailbox, and checking the mailbox is expressed by the receive construct. In receive, you have a typical functional programming style where you express a particular condition, and if this condition is fulfilled, then you evaluate new expressions. So the expressions after the arrow in this example are basically the activities you would like to do on the receiving of a particular message. Before the arrow, you see something that is very common with actors, and this is checking the mailbox with pattern matching. So instead of doing an explicit receive operation for example, for a particular message tag or for a particular source, you just take the mailbox as it is in the moment of the execution of the receive block, and you scan several patterns in order to see if such a message is available in your mailbox. You can also have default clauses here with the other clause where you can express particular activities when none of the patterns is matching. But the basic point, the crucial idea here is that this pattern matching is not depending on the ordering of reception. So independent from the fact how your messages go into the actor mailbox, the pattern matching will find the message if it's there or not. So all kinds of race conditions we saw that mainly depend on the order of reception of information can be avoided by this, because you no longer depend on the ordering of reception. You just say, I have a couple of messages that are already received. If the interesting message is in there or not, I can check by one statement. If this is not the case, maybe I have something else to do. So this is a very crucial idea of the actor model, and it's one of the reasons why actors are very, very good to at least avoid race conditions. So actor support helps you in dealing with the typical concurrency issues you may have. So here's a larger example with Erlang code. Without understanding all the details of the Erlang syntax, you can see here by the explanations that this is a combination of two actors, the ping and the pong actor. So the idea is to have a ping pong game where both actors exchange messages for a while after they reach the limit. So you see here that on the lower part we have the start code that's firing up the ping and the pong actors in their first instances. And then the pong actor, for example, has first a receive block, and in this receive block it checks for two kinds of messages. Either it gets a finish message, which tells the pong actor that the overall application activity is now over, or it gets a ping message from a particular ID, which is the actor ID, and then it prints out a statement and sends back the result to the original sender of the message. So you can easily implement some request-response pattern here if you like to, although you have the mailbox concept and the asynchronous send concept. Erlang works with recursion, so for example the pong actor is using recursion in order to have a repeated reception of incoming messages. This is a very typical idea in functional languages which relies on the tail recursion. It's basically some detail of the language here. The main thing you need to take away from this slide is that writing actors is the usage of basic primitives for scanning your mailbox for particular message patterns and for sending asynchronously data to another actor that is identified by its PID. Another language that implements actors is Scala. You saw that already in the earlier weeks. And here you have a very similar syntax to what we saw in Erlang. The idea again is to define an actor and to have a loop, and inside this loop you do a continuous reception of messages. You scan the mailbox for a particular pattern. In this case, this is done by something that is called case classes. You see here data and getSum are instances of a particular class, of a special kind of class, and these instances express a certain message type. So message types are no longer defined by doing explicit message headers and specific bytes as you would do in low-level languages as, for example, C. Here you define classes and you use these classes as your message type. And on the reception part, you just scan for the message type, see if you have it in your mailbox, then you take the message, you read the content, and you react on this. And maybe as a result, as here with the getSum message, you do another output operation where you send some value to the requester. In Scala, we have another advantage, which is that all of these primitives are library constructs, so they can be exchanged. Scala has a very performant implementation of actors called Akka, which now becomes part of the language itself. And this allows you to do large-scale Scala applications based on actors, where you can leverage your processing elements in parallel in order to give it some speed up. Here's another more complex example in Scala. You see that we have an application class which starts a counter actor and then sends continuously increment messages to this counter actor. And after a while, it sends a value message, which means please give me the result of your counting, and then it prints out the value. The actor implementation itself has an act method, and in this act method, we see the typical receive block where we take the value or the received message and take the value out of it and then do some work with it. So the pattern is very similar in the different languages, and the crucial advantage is the understanding of having asynchronous communication, both on the sender side and with the matching approach for the mailbox on the receiver side. If we come back to our original discussion of concurrency issues and parallelization issues, you can ask again yourself, can we have deadlocks here? And in Scala, this is possible. For example, Scala has a synchronous send operator, which slightly derives from what we know from the actor concept. So in the original actor concept, sending is asynchronous, so it returns immediately. If you use synchronous send in Scala, as you see in the upper part example, you send out a message, and after that, you immediately wait for an according response. This is very helpful when you want to implement request-response patterns. So you may think that this is a very good tool and it allows you to write shorter code, but it has the danger of deadlock. So if you look into this example, we have the situation that you have actor A and B. Both are sending a message and wait for the according response message, and they have the potential to block in this attempt. So if you want to work with actors, it's typically a good idea to really model your parallel application, your concurrent application in a way that you use the original actor idea. So you see this in the lower part of the slide, where we truly do an asynchronous send on both sides and both actors, and then start to do the blocking receive loop, where we explicitly wait for a particular message to come in order to continue our control flow. So if you consider these things, they are well described in the different language tutorials, then actors can be a very helpful tool in order to write parallel and concurrent applications in larger scale for a shared nothing environment.